Our result we've been looking at is the work kinetic energy theorem, and it says the net work done by all forces, as the net always means by all forces. So the net work done on an object during its motion is equal to the change in kinetic energy of the object between the final and the initial, if the system we're looking at behaves like a particle. Okay, so now let's try to apply that in two different ways. The first thing we'll do is some voting questions having to do with this. This one's about the definition of kinetic energy. We drop two marbles. One is twice as massive as the other. We drop them at rest from a roof and let them fall to the ground. And the question is, what's the relationship between their kinetic energies just before they hit the ground? Okay, how does the heavier marble relate to the lighter marble's kinetic energy? Are they equal in kinetic energy? The heavier one has twice as much, half as much, 4 times as much, or impossible to determine the relationship compared to the lighter one? The answer is twice as much. This is just looking at the definition of kinetic energy, 1/2 mv squared. We know if we drop something from the roof of a house, drop a marble, air resistance can be pretty negligible, and therefore they'll have the same speed when they're about to hit the ground because their acceleration is the same. They're in free fall. So they both have the same speed when they're about to hit the ground. They hit the ground almost at the same time, right? And in 1/2 mv squared, the v is the same right before they hit the ground, but the m is twice as big for the more massive one, and therefore twice as much kinetic energy is the correct answer for the heavier one compared to the lighter one. Second question. Spaceship is initially moving at 400 meters per second toward the galaxy Alpha Centauri in deep space. There's no sources of gravity there, so the only force that's going to act on the spaceship is when it fires its thrusters. We'll imagine the spaceship is initially aimed away from Alpha Centauri, and it fires its engines, or its thrusters, constantly for 2 minutes with the thrusters aimed toward Alpha Centauri. That's going to try to get it to start moving away from Alpha Centauri. It takes 2 minutes, but it goes from going at 400 meters per second toward it to 400 meters per second away from Alpha Centauri after 2 minutes of firing the thrusters. Okay, those are our initial and final states. What can you say about the work the thrust force did on the ship during this period? And the answer is down, so the answers are positive, negative, or 0 work done by the thrust force. I made a mistake and put net work down there, but the answers are supposed to refer to the thrust force, not the net work. The answer, surprisingly to some, is 0 in this case. It might seem like it's not 0 because the thrusters are firing in the same direction the entire time, but one way to think about this is through the work kinetic energy theorem. In this case, the work done by the thrust is the only work acting on the ship as it fires its thrusters, and therefore the net work is the work done by the thrust. The net work is equal to the change in kinetic energy. It started and ended at the same speed, and so it didn't change its kinetic energy between initial and final. And so 0 net work was done. That also means the thrust force, which is the only force, did 0 work. The net work is the thrust force work. Let's change the question slightly. What if we reduce it to how much work did the thrust force do only during the first half of this 2 minutes of firing? Positive, negative, or 0? In this case, the answer is negative. In other words, the ship is still in the first half of this thrusting period. It is moving still toward Alpha Centauri, while the force on it from its exhaust is oriented away from Alpha Centauri. And whenever a force is directed opposite the direction of the displacement, we get a negative work. And that's so the thrust force is doing negative work during the first half of this period. It would be positive work if I had asked about the second half of the period. One more voting question. Car starts from rest and accelerates to 30 miles per hour. Later on, it gets on a highway and accelerates from 30 to 60 miles per hour. Which takes more work, the 0 to 30 or 30 to 60 miles per hour, or are they both the same? This is also somewhat confusing. A lot of people think it should be the same because the change in the speed in both cases is the same, but it's bigger for the 30 to 60, and it comes from in work kinetic energy theorem, which takes more work. Well, which one has a bigger change in kinetic energy? It's that v squared in 1/2 mv squared. That means if v gets a little bit bigger, v squared gets a whole lot bigger. And so that can make it so that it's not sort of equal. Even though the change in speed is equal here, the change in v squared is not the same. The force that's doing the work on the car is the road ultimately, right? If we think of the cars as being the wheels as being part of the car, as the car is speeding up, it's trying to push the road backwards behind it. The road is pushing forward on the car, and it's doing the work on it. But in this case, we can sort of simplify it by taking different numbers in it. So we're going to use the net work. The work done on the car by all the forces is just the work done by the road in this case. It's equal to the change in the kinetic energy. And let's take a simpler case where the mass of the car is 2 kilograms. That means I chose that because then 1/2 m is 1 in SI units, so I don't have to worry about the 1/2 m. And so I just have to calculate v final squared minus v initial squared, and let's do it for 0 to 1 meter per second versus 1 to 2 meters per second. For 0 to 1 meter per second, I do 1 squared minus 0 squared, that's just 1 joule. For 1 to 2 meters per second, that's 2 squared minus 1 squared, that's 4 minus 1, or 3 joules. So the answer is, when you're already going fast, it takes more work to go just that much farther, faster than you were going before. And one way you might think about this is when you're at rest at a stop sign and you start accelerating, it's very easy to change your speed. But once you're going at 80 miles per hour down the highway, it's not easy to go a little bit faster. And so it would take a lot of work to speed you up just a little bit at that speed. That's one way to think about why it's kind of hard to speed up once you're already going fast. All right, we'll take a little break, but I want you to do problems 3, 4, and 5 on the worksheet right now. Here's problem 3, but I'm going to turn off the video in a second. It starts out, it's actually got parts A, B, and C, but there's a 1/2 kilogram ball. We drop it from rest at the top of a skyscraper, and the ball falls a long distance, but in the first 400 meters, after that it's fallen 400 meters, it has a speed of 20 meters per second, and it's very close to its terminal speed at that point. That's telling us that the air resistance force, or drag force, is definitely not negligible during this motion. So keep that in mind as you answer parts A, B, and C. A says, or asks, what net work is done on the ball during these first 400 meters of falling? Okay, try problems 3, 4, and 5, and then come back to look at the solutions.